Hey, AP Calc students, we're going to do a quick lesson on U-substitution. So U-substitution allows us to work um, with a function f of x and changing it to a function of u so we can more easily find the antiderivative. Um, Remember that if you're going to derive something like this, you would have chain rule, same thing here, same thing with this one. We would have to account for that. So if we're deriving this, we're actually going to be working backwards using U-substitution to anti-derive and kind of account for those pieces that would get attached on through the differentiation process. So the first thing I'm going to do is try to make this more simple. U is going to be equal to x squared plus 3. That way, I can put this as u to the 8th power. The problem with that is we have 2x and dx, and we have u's. You can't have u's and x's all at the same time to find the antiderivative here. So what I'm going to do is I'm going to find the derivative of u with respect to x, and that's going to give me 2x. And I'm going to move the dx over, so du equals 2x dx. Through rearranging this, I notice now that wherever I see x squared plus 3, and x squared plus 3, I can substitute in u for that. So u to the 8th power. Wherever I see a 2x dx, I can substitute in a du for that. This quickly becomes something more manageable. I have u to the 8th power du. Again, here we have u is x squared plus 3, so wherever I see that, that's going to get a u to the 8th power. Here's my 2x right there, multiplication dx using substitution, 2x dx becomes du. Now I find the antiderivative is u to the 9th plus c, and I just can't leave it in terms of u. I have to go back and substitute in my u. So x squared plus 3 to the 9th power plus c. Apologize. U to the 9th over 9. My apologies. Over 9. Perfect. If we want to check our work, we go to derive this. The c is going to go away. You would get 9 of these to the 8th power. The 9s would go away. And then when you attach on the chain link, x squared plus 3 would be 2x. So the antiderivative of that, like I said, the derivative of that would be this to the 8th power all over 9 times 2x. And that goes away. Boom. We are all set. So step 1, choose the inside longer expression. Do some side work to find u, find the derivative du dx. Rewrite the integral u and du. Integrate in terms of u. Substitute the expression back into u. Alrighty, so let's try to tackle one of these other ones up here. Let's take this one for right now. So I'm going to call u x minus 8 because it's a little problematic under there. So du dx is equal to 1, or du is equal to dx when I find the derivative. So I adjust for my dx, which is great. I now have u to the 1/3 power because of all of this, because the x minus 8 is a u now. The problem here is I have 2x, so I still want that to be in terms of u. What I need to do is I need to say that x is equal to u plus 8. If I move 8 to the other side, I can solve for and isolate my x. So this whole thing changes into the integral of 2u plus 8 u to the 1/3 du. We're going to distribute, we'll get 2u plus 16 u to the 1/3 du. Distribute again. We're going to get 2u to the 4/3 plus 16u to the 1/3 du. Whoops. All right, so the antiderivative is 2u. We add 1 to the exponent, so that's 7/3 divided by 7/3, plus 16u to the 4/3 divided by 4/3, plus c. We have 6u to the 7/3 over 7, plus, that's going to be 48, 16, yeah, so 48 fourths. So we're going to say that will actually simplify to be 12u to the 4/3 plus c. And I just have to substitute my u back in, which is x minus 8. So it's 6x minus 8 to the 7/3 over 7 plus 12x minus 8 to the 4/3 plus c. So it seems that, that substitution might not have been required here, but don't forget you have this x minus 8 to the 1/3, and that's pretty problematic. You got to make that more simple and bring that simpler idea, the u, to the 1/3 power, which allows us to combine with the 2x. A lot of work. I'm going to run out of room, but we'll do a couple more. I'll do one more here. We have, I'm going to call u 3x plus 4, du dx equals 3. Notice I'm picking the item that's a little bit longer, that will simplify to try to get me the additional information that's there. Like I see this 3 right here. How can I get the 3? If I derive 3x, I get 3. That's where I was looking to set this denominator to be a u. So when I find, so I'm going to say that this is going to be 3. So du equals 3 dx. Well, that's great. This integral now becomes 3 dx, which is du, over u. Or let me just say it's 1 over u du, if that's a little easier to see. It doesn't matter. I could have left it as du over u. The antiderivative is ln of u plus c. So the ln of 3x plus 4 plus c. There we go. And if I derive it, I'll still get what I originally started with. Okay, so we're making good progress on these. This one, it would be u would be 2x plus 2. Du is 2 dx. Instead of dividing both sides, dividing the left side by dx, I'll just immediately put it to the other side. So you have e to the u du after we substitute in for both parts. And the antiderivative of e to the u is e to the u. Excuse me. Yeah, so e to the u plus c, my bad, plus c. So when we rewrite this one, we have e to the 2x plus 2 plus c. Don't forget, if I derive that, you would have had the chain link of attaching on. So it's e to the u times the ln of my base, which is e, so 1. Ln of e is 1, times the derivative of 2x plus 2 is 2. All right. We can do more of these, but we'll go on to, I'll let you practice those. You know what? We'll do something like this one, because this one doesn't have a perfect setup. So u is equal to 2x squared. Du dx is equal to 4x. We're going to have to rearrange it. I want just an x and a dx. So I'm going to say du equals 4x dx. 1/4 of du is equal to x dx. So now I can see the 1/4 is showing up here. So the x dx is 1/4 du. So we have the integral of cosine of u times 1/4 du. The 1/4 can go up front, it doesn't really matter. The antiderivative cosine is sine, so sine of u, it's 1/4 of it plus c, so 1/4 sine of 2x squared plus c. If you derived it, you would have sine would become cosine, the 2x squared would stay, you would multiply by 4x as your chain rule, and that's where the 1/4 of 4 go away, and the x would stay. All right. Let's go on to definite integrals with U-substitution. The only difference here is that you need to change the order of your limit. You get to change your limits if you're not going to resubstitute in. So here's what I mean to say. I'm going to call u 1 minus r squared, so du dx equals negative 2r. I'm going to adjust this, so du, oh, sorry, I meant dr here. Dr, my apologies. This is equal to negative 2r dr. I have an r dr. I don't want the negative 2 there, so I'll divide both sides by negative 2. So negative 1/2 du equals r dr. There's my r dr. Now, there's two ways to do this. So I'm going to say that this is u, the square root of u, negative 1/2 du is my new integral. I could also have written this differently. I could have written as u to the 1/2. You know what, I'm going to do that just because it'll all be set up and ready to go. We're going from 0 to 1. The problem here is that if I don't substitute in my r's back in, I don't necessarily have to, but I would have to change this right here and this, both limits of integration. Because in terms of u, I just take my u and I say u is equal to 1 minus 0 squared, so u equals 1. I can also take my u and say u is equal to 1 minus 1 squared, so u is equal to 0. So wherever I see a 1, I place a 0, and wherever I see a 0, I place a 1. That means I don't need to change anything. I can leave this just in terms of u when I find the antiderivative. So change my order of integration. I'll make that a negative. But there's already a negative 1/2 in there, so I'll just make it a positive. And then I have u to the 1/2 to u. The antiderivative of u to the 1/2 is u to the 3/2 over 3/2. There's a 1/2 out front. Reevaluating it at 1 and 0. So this changes into 1/2 times 2/3, so that's actually just 1/3 u to the 3/2 when I simplify the fraction over fraction, or the denominator being a fraction. So I'm going to do 1 to the 3/2, whoa, a third of that, take away a third of 0 to the 3/2. 0 to any power 0, we have 1/3 as our final value. 1 to any power is 1. Now it was kind of hard here because my 0 and 1 ended up being a 0 and 1. It doesn't always work that way. If I were to do pattern 2, I could have ignored the changing of my upper and lower limit. So let me go back and do it a second version. So here's version 2. Let's say all I did was the work in red here, okay? I would then just ignore my bounds and my limits. I would just write it 0 to 1. My RdR becomes negative 1/2 du, and then I have u to the 1/2 power. I'm going to leave the negative 1/2 here. I'm going to find the antiderivative. So negative 1/2, the antiderivative u to 1/2 is u to the 3/2 over 3/2 from 0 to 1. But again, these aren't the right numbers at the moment. Let me just leave that off. I'm going to clean this up. I get negative 1/3 u to the 3/2. What I need to do is I need to substitute in my r's back. So I'm going to say negative 1/3 1 minus r squared to the 3/2. Now I can do that from 0 to 1. My original 0 and 1, not anything I adjusted with the upper and lower bounds or lower limits. So do all this work. We get negative 1/3, 1 minus 1 squared, all to the 3/2. Take away negative 1/3, 1 minus 0 squared to the 3/2. We're starting to see the same thing happen here. 1 minus 1 is 0. 0 to any power is 0 times negative 1/3. That's just 0. I have a double negative here. I have a 1/3. That's going to be 1 to the 3/2. We still end up with a result of 1/3. It traditionally we rewrite and do what's in purple, but you can do what I did in orange. It just tends to be more work. Normally we used u to simplify the problem, and to reintroduce my r's back in becomes a little bit problematic just with the amount of work we have to do. We want to keep it short and sweet and simple if possible. Let's try another one where it would be more prone to just change our u out. This one, we have a lot going on here. Let's do something, maybe let's do this next one. Yeah, so here, u I'm going to call x plus 2, so du equals dx. So I have the integral from 0 to 7. Oh, what I'm going to do now, before I even do that, I'm going to say u equals 0 plus 2, so u is equal to 2. So now my lower limit is a 2. So u equals 7 plus 2, so u equals 9. Now my upper limit's 9. So I'm changing my 0 and 7 to 2 and 9. I find the integral from 2 to 9 of 1 over u du. So the ln of u from 2 to 9. So ln of 9, take away ln of 2. I don't need to resubstitute in my x plus 2 for my u. And that's it. I mean, we can probably simplify ln of, I think we're just going to write it as 9/2. Let me just see if what's equivalent here. So ln of 9 minus ln of 2. Is it the same thing as ln? Yeah, so we can just write it as ln of 4.5 using my rules. All right. And they're all positive, so we're good to go. Now again, if you wanted to, you could have left the 0 and 7. Once you find the antiderivative, you would say that's ln of u and the ln of x plus 2 from 0 to 7. Well, using your old 7 to 0 bounds, it would be ln of 9 minus ln of 2. Same exact thing that we had before. All right, and this last one here, let's see. This one's a doozy. We're going to say u is equal to 3x squared plus 12x plus 1 du dx equals 6x plus 12. Du equals 6x plus 12 dx. Factor out a 6 and divide it out. So 1/6 du is equal to x plus 2 dx. That's looking pretty good right there. That's your x plus 2 dx. But we're going to have to change our numbers because I want to keep it in terms of u. I don't want to go back and substitute these x's back in. So u is equal to 3, 1 squared plus 12 times 1 plus 1. So u is 3 plus 12 plus 1. My new u is 16. My other new u equals 3, 0 squared plus 12, 0 plus 1. That's really nice. U is 1. So this is 16 and 1 now. Notice I'm putting them in the same order, in the same placement. So my integral now is 1 to 16 of, let's see, x dx. That's 1/6 du. And then it's u to the 1/2 power. You can move the 1/6 outside, and then we'll just say it's u to the 1/2 du. That's really nice and clean from 1 to 16. Now that's going to be 1/6 u to the 3/2 divided by 3/2. From 1 to 16. I don't need to go and do anything else. There's no substituting needed. 2/3, 3/2 divided by will be times 2/3. That's gonna be 2/18 or 1/9. So it's gonna be 1/9 u to the 3/2. And look at my numbers, 1 and 16. That's really nice. We're gonna do 1/9 the cubic root of 16. What do we got here? I'm sorry, the square root of 16. Sorry, square root of 16 cubed. And we're going to take away 1/9 of the square root of 1 cubed. 4 times 4 is 16 is 64/9. Take away, that's going to be 1/9. So 63/9. 63/9. Which is going to be 7. Is equal to 7. And we can check them in our graphing utility calculator if we want to. This one's looking pretty good. So the accumulation from 0 to 1 of that is 7. All right, that's it for U-substitution.